So I now want to turn to problems where we're not interested just in a nonlinear relationship between y and one independent variable, but between y and multiple independent variables. So far we've considered various approaches for flexibly modelling the relationship between y and a single covariate x. These are extensions of simple linear regression, as we've shown. But we want to now look at the problem of flexibly modelling y on the basis of several covariates, which amounts to an extension of multiple linear regression. And the way that this is done, and it's not really, it really just is a way of additively combining what we've seen before. It's what's called generalised additive models. They provide a general framework for extending a standard linear model by allowing nonlinear functions of each of the covariates while maintaining additivity. And just like linear models, GAMs can be applied with both quantitative and qualitative responses. So when we say a generalized additive model, this is important because it relates to the fact that we can use, it can extend generalized linear models as well. It's not just for linear models. We'll first look at how GAMs extend the standard linear model, and we'll then look at how they extend the generalized linear model by introducing specific link functions. So a natural way to extend the multiple linear regression model is, in order to allow for nonlinear relationships, is simply to replace each linear component beta j xij with a smooth function. We'll call it fj. So we can then write this model in this form here, additively, because it's a generalized additive model, because we're calculating a separate function for each x, and then we're going to add together each of the contributions. But what this of course means is that the nonlinear function that we estimate for x1 is conditional on the nonlinear functions that we've estimated for x2 up to xk. So in 9.4 we discussed many methods for fitting functions to a single variable, and with GAMs we can simply use these methods as building blocks for fitting an additive model. And in fact, most of the methods we've seen so far in this lecture, for instance regression splines and natural splines, we can just do this fairly trivially to represent each of the functions for each xj, for x1 up to xk. We can just use these procedures to represent each function for each x, and then we add these together. Now it turns out that the GAM with smoothing splines is slightly more complicated. We have to use an approach known as backfitting, and you can read a bit more detail about that there. But we don't need to worry too much about that now. In principle, what we're going to do is just use the methods we've done previously, but we're going to estimate each function of f. We can use a natural spline or a regression spline, and then we're just going to add them together, and that's how the GAM works. So it's really a straightforward extension of what we've seen. Now just to make the point that this isn't just for linear models. Recall that the generalized linear model we talked about previously, each observed outcome is assumed to be generated from an exponential family distribution, so we can model many different types of distribution. The conditional mean of this distribution depends on the independent variables through this expression here, where g is the link function. This is the expected value of y conditional on x, and x beta is the linear predictor. We saw that previously. So GAMs are simply going to extend GLMs by relating the expected value of y to the covariates through the link function, or in this case the inverse link, but it's with smooth functions rather than, so a sum of smooth functions rather than in terms of a usual linear predictor. And in the same way that a penalized spline can be estimated as a mixed model, GAMs can be estimated as a generalized linear mixed model with the basis functions appearing within the design matrix Z and the smoothing parameters as variance components to be estimated. So I don't really need to say much more about GAMs than that, because the basic principles have all been covered in the case of a single covariate. Just to summarise, the main advantages of GAMs are as follows. They allow us to model or to fit a nonlinear function to each x, so that we can automatically model nonlinear relationships that a linear regression might miss. The nonlinear fits can potentially make more accurate predictions for the response. And because the model is additive, we can examine the effect of each xj on y while holding all other variables fixed, so it's still got that conditional interpretation. And the smoothness of the function for the variable can be summarised via degrees of freedom. The main limitation is, of course, that the model is restricted to be additive, and therefore with many variables important interactions can be missed. Nevertheless, as usual with a linear model or an additive model, we can manually add interaction terms to the GAM by including additional predictors of this kind of form or low-dimensional interactive functions of this form. So it actually provides a very flexible fit, as we would imagine by Taylor's theorem. Okay, last example I'm going to cover in the lecture. Same data. We're going to use a GAM to fit to this data. So what we're going to do is fit to two covariates rather than one. Now we're going to say we're not just interested in the relationship between Knox concentration and temperature, but we're interested in the relationship between Knox concentration, temperature and wind speed simultaneously. Before proceeding, let's look at a scatter plot of Knox wind speed data just to see what the relationship looks like, and we've got it here. And the scatter plot suggests that the second relationship of interest is also non-linear. And this makes sense scientifically due to the sort of complex interactions that we have from dispersion and dilution and turbulence and mixing. Again, we don't need to worry about these, but there's good sound scientific reasons to assume that the relationship between Knox concentration and wind speed is non-linear, and this is indeed what the scatter plot tends to show. So we're going to fit the following GAM. We're going to fit one in which we use natural splines to approximate these smooth functions, and another where we use smoothing splines. So we load the GAM library. It's library in R called GAM. Reload the data, clean the data up. That's just the code for our scatter plot that we saw here. Fit a GAM with natural splines, that's the NS command. And we're going to fit a GAM with smoothing splines using the command S. And this gives us a summary of the results. Again, not greatly of interest a lot of the time. We're interested mainly in what the fit looks like. But I do just want to draw your attention to a few things. We get these ANOVAs for parametric effects and ANOVA for non-parametric effects. And what the ANOVA for non-parametric effects tells us is the p-values are small, clearly demonstrating that both temperature and wind speed are highly statistically significant, even when we only assume a linear relationship. Moreover, the ANOVA for non-parametric effects, the way to interpret this is the small p-values for both temperature and wind speed provide very clear evidence that non-linear terms are required for these covariates. So in other words, the non-parametric effects are adding value to the model. Next, we can plot the fitted model, and the GAM package makes this very easy using this notation here. And first of all, this is the natural spline, and then we have the smoothing spline, and as you can see, the diagrams look very similar. Let's deal with the diagram on the left. This is air temperature on Knox concentration. It shows the relationship between Knox concentration and air temperature, and the shape of the estimated curve is essentially consistent with those we've looked at previously in the lecture, so we get the same kind of answer. The figure on the right in both of these diagrams shows the relationship between atmospheric Knox concentration and wind speed, conditional on temperature because it's in a GAM where we've got more than one covariate. And as expected, the estimated relationship exhibits significant non-linearities. The atmospheric Knox concentration declines rapidly with increase in wind speed up to a certain wind speed, beyond which the decline becomes more gradual and actually a lot more variable in this part of the data. The last thing I want to say really is that we've now used various different methods to estimate this relationships in the GAM data, and actually in this particular example they've all given very similar results, and that is kind of quite nice smooth curves that take this kind of shape. In other relationships where things were much more non-linear, where things were naturally more wigglier, we wouldn't necessarily find this. So we might find that a global polynomial fit actually doesn't do justice to the data. And you can see this slightly here where we get these bumps in using a more flexible form, but it might be more obvious in other data sets where nonlinearity is really substantial.